Hello, AP Physics. I'm going to improvise a little bit as I make this video. It's guessing going to be kind of on the long side, but I need to head home as soon as I can, so I don't have time to make a careful version. What I want to talk about is something called an RC circuit. This is a circuit that contains both resistors and capacitors, unlike the circuits that we've seen so far, which have one or the other. The reason that RC circuits are important is that they have a time-varying behavior, unlike circuits that contain only resistors, where they have like an on state and an off state, and they just transition immediately between the two. And a circuit that contains only capacitors, if we idealize it, at least a circuit containing only capacitors also reaches its steady state like instantaneously. So that steady state would be like when the capacitors are at their full charge or whatever. But if there is resistance in the circuit, then it takes a certain amount of time for the capacitors to charge up instead. And that amount of time is, how do I put it? I'll show eventually that it's based on like an exponential function. They charge most of the way pretty quickly, but then they get slower and slower and slower as they reach their maximum value. And the same kind of thing happens when they discharge, when you empty them out. So, got a diagram here that has the resistor and the capacitor that I already marked. I'm going to go ahead and write an R and a C. That's where the name RC circuit comes from. And there's also a battery. I'm just going to give it an EMF symbol. And then up at the top, this funny line that's just floating by itself is a switch. So the first thing that I'm going to do is move that switch over to the left. So I'm going to go ahead and erase the line that's there. So I've now connected the switch, which creates a loop on the left-hand side of the circuit, so that current can flow around the loop that way. Conventional current is going to flow that way. So when I do that, positive charges accumulate on the top plate. Those positive charges repel positive charge away from the lower plate, which leaves the lower plate with a negative charge. And that's the process by which capacitors become charged. We've already talked a little bit about capacitors in isolation. So if you look at, erase all of those. If you look at the charge of the capacitor as a function of time, assuming it starts at Q equals 0, you're going to find that it behaves something like this. So it's moving up towards some maximum value, asymptotes to that maximum value. The initial rate of change is pretty strong. That's because when the capacitor is empty, it's easy to put a few extra charges on the plates. But as charge accumulates on the plates, it gets more and more difficult to put more charge in, because if I'm trying to shove an extra electron onto that negative plate, there's already a lot of electrons there, so it's going to take more force or more effort or more work, however you want to sort of qualitatively think about it, and that means the rate slows down. And it continues until you reach whatever this maximum Q is going to be. The maximum Q is based on Q equals delta VC, which is that's basically the capacitance definition that we saw earlier. And the delta V in this particular case is going to be the EMF of the battery. But in a more complicated circuit layout, the delta V might not necessarily be the battery. voltage, it might be something else. But it's the delta V that like we're moving toward, basically. So if I move the switch over to the other side, now the battery is no longer part of the loop. It's been cut out. But I have this other loop that goes around on the right side of the circuit. And remember, I had a bunch of positives on the top plate, and I had a bunch of negatives on the bottom plate. And so as soon as I provide a pathway for all of those charges of like sign to move away from each other, they're going to move away from each other. So when I flip the switch over, current is going to flow the other way to discharge or neutralize the plates. And if we look at the charge during the discharge process, discharge, I start at some initial value for Q. At the beginning, when there's a lot of charge on a plate, there's going to be a pretty strong electrostatic force pushing the charge away. And so the initial rate of change is quick. But as the plates empty out, the force that's being applied gets weaker and weaker, and so the rate also decreases. So in both of these cases, I have an asymptotic behavior, either towards the maximum charge or towards zero in this case. If you think about, so I don't know how to put this. If you think about the initial charging behavior, so I'm talking about like the very first instant when I start charging. The capacitor at that point is empty. And it effectively acts like a regular wire in that first instant. So for example, the initial current, I could calculate just from the EMF and the resistance. I can ignore the capacitor completely. I just pretend that's actually a wire. That means that the initial current is going to be E over R. I don't have to think about it. The final charging behavior this refers to when there's basically not any charge flowing anymore. In the final charging behavior, the capacitor is full. I'm going to put full in quotes because the meaning of full depends on the voltage applied, not just on the capacitance of the capacitor, but it's reached its like maximum state. That full capacitor acts like a break in the circuit, or a gap, or an open switch. So basically current can't flow because there's a break in the circuit. That's why the current goes to zero. And those two ideas, that empty capacitors, completely empty, act like wires, and full capacitors act like breaks. Just that idea will get you pretty far in a lot of the questions the College Board likes to ask about RC circuits. They will often ask about the initial and final behaviors of the circuit. And as long as you can keep those ideas in mind, empty capacitors are like wires, full capacitors are like breaks, you'll be able to answer a lot of those questions. Okay. So I'm going to write a couple of equations here. I'm going to drag some of my stuff around a little, make some space. Uh-oh. Actually, I don't like that place. Let's move all of this stuff down. I caught like 1 pixel of that axis. Okay. So this charging graph, the function that describes that, I'm going to write below. I will derive this later. Function has a pretty simple form. So there's a coefficient in front, but that coefficient is just the maximum value. And then I have 1 minus e to the negative stuff. E to the negative stuff itself is a decay function. It would look like the lower graph. So I'll go ahead and write that one in also. The decay graph has a simpler mathematical form. Here it's q of t equals q naught times e to the negative t over rc. So e to the negative stuff is that decay graph. 1 minus e to the negative stuff is this growth graph instead. And the stuff is of some interest. There's a little t divided by rc. So the r and the c, sometimes people will write a tau instead. RC is the time constant of the circuit. So the idea is that when little t is equal to the time constant, when little t is equal to RC, then you have e to the negative 1. So the time constant represents the amount of time that you need for that exponent to become a negative 1. It starts out at 0, at time 0. And then as time goes by, the exponent becomes more and more negative. RC, or the time constant, is the amount of time that it takes for it to become 1. So the larger r times c is, the more time it takes to reach an exponent of negative 1, and therefore like the more stretched out horizontally the graph gets. A larger time constant means the process is slow. A fast or a short time constant means the process is fast. This is similar in a lot of ways to half-life when you talk about radioactive decays and that sort of thing, but it's a little more complicated because this is with a base E instead of a base 2, for one thing. And with half-life, you get decays from your initial value, but you never have a growth. And right now I'm showing you the simplest possible RC circuit where either the initial or final value is 0, and they don't have to be like that. With half-life, it's always a decay towards 0. But with RC circuits and the time constant, you don't have to have 0 on either end, and it could be either end when it's there. So it's a little more complicated than half-life, but the same like basic idea is there. Okay. I think that's all of the starting info. That's like the overview. Grab a copy of this circuit for my next page. So I want to show you about the process of getting that equation, getting the exponential equation. This is something that the College Board might ask you to do, and I want to emphasize that the formula sheet for the exam does not have the time constant listed on it, so you have to remember that the time constant is r times c. And the formula sheet also doesn't have those exponential functions on it. Now, frequently, they're only going to ask about the initial and final behavior anyway. And if they ask about the behavior at some other point in time, such that, I flip back, like if they wanted to ask about this moment in time here, you'd have to calculate that point. You would need to use the function to do that. But the initial and the final values are easy. You don't really need the exponential for those. So it's only in the process of going between those extremes where you need the exponential function. But they might ask you about that, or they might ask you to derive it because it involves a differential equation, and they love differential equations. So I want to talk about the discharge process. The classroom next to me is playing CNC music machine. Anyway, the way we start the derivation for the discharge is to imagine doing a Kirchhoff loop. So I want to make a loop that goes around the circuit this way. Keep in mind that the capacitor plates are charged like that. And I know that during the discharge process, the current is going to go the same direction that I drew my loop, because it leaves the positive plate on its way to the negative plate. So if I write out a loop, I can say 0 equals minus IR plus Q over C. So the minus IR is the potential difference for the resistor when a current I flows through it. Q over C is the potential difference for a capacitor that has a charge Q inside it. So I've got that statement. What I'm going to do is replace the I. Remember that current is a flow of charge, so there's a relationship between I and Q. This part is a little bit non-intuitive, but I need a minus sign here. The reason that I need that extra minus sign is that the letter Q in this equation doesn't refer to like generic charge with no specific meaning. It is specifically the charge on the positive plate of the capacitor. So during the discharge process, Q is a quantity that's going to be decreasing because it starts out positive and it's moving towards 0. So dQ dt, where Q refers to the charge on the positive plate, dQ dt is negative, but I want this potential difference term for the resistor, like I want that term to be negative. So like this minus sign combined with the decreasing dq dt would like mess things up. But if I put that explicit minus sign in, those minuses cancel. The quantity dq dt is negative, and so everything is the way it's supposed to be here. So if you rearrange this and do a separation of variables, you can get it in a state that looks like dq over q. No, wait, I don't want to do separation of variables. I'm lying. I'm just going to get the dq dt by itself. dq dt is q over rc. And remember, q is a function of time. So what this is telling me is that the derivative I have some function q, and the derivative of that function q is a constant times the original function. Okay? This is basically saying f prime equals c times f. The function that we all know that behaves that way is e to the x, or e to something. It's going to be e to the, like the c comes out from doing a chain rule. So this is the differential equation. The solution to that differential equation is for q of t to be some initial value, q naught, times e to the negative t over rc. I messed something up with my minus signs. What did I do wrong? Oh, yeah, there will be minus sign. Let me explain why I paused there. These two minus signs here, I knew they were going to cancel out, and so everything was positive, but when I solve for dq dt, I have to move something to the other side of the equation, so there's not a zero there anymore. That's why there should be a minus sign. So the minus signs there become the minus sign in the exponent. Okay, so that's the function for q. Suppose you want to know the function for delta V of the capacitor. I'm going to put a little subscript C on here, so you know that's the delta V for the capacitor. Delta V for a capacitor is supposed to be Q over C. Well, I just found out Q is a function of time. So delta V as a function of time is going to be Q naught over C, e to the negative t over RC. And of course, Q naught over C, I could also write as delta V naught if I felt like it. So it's basically the same function. All I had to do was change, if I want to change the Q to V, I just change the other Q to a V also. I get the same thing. If I'm interested in the delta V for the resistor, let me get the current first. Suppose I want to know about the current. I know that current is negative dq dt. I used that earlier. So that means that the current is going to be negative Q naught times e to the negative t over RC. And then I chain rule, gives me negative 1 over RC. So the current is positive Q naught over RC. Q naught over C is delta V naught. So the current as a function of time is delta V over R, which would be the initial current, times negative T over RC. So I could write that initial current as I naught if I don't like it. So hopefully you are seeing a pattern here that basically everything has the same function. The one difference would be if I was interested in the delta V for the resistor. Delta V for the resistor is I times R. And, oh no, that's the same thing also, because I is the function I just got. So I'm going to have I naught times R times e to the negative T over RC. I naught times R, you can think of as being delta V naught. I should put another resistor on there. I'll go back and put a capacitor subscript on the other one. Basically, they're all the same thing, is my point. For the discharge case, at least, they're all the same thing. But the way that all of this comes about is a Kirchhoff loop rule. Just write the loop rule for some arbitrary point in time. I know that the potential difference for the resistor has to be IR. I know the potential difference for the capacitor has to be Q over C. Then you relate the I to the Q. And from that, you can conclude there's this exponential decay form. Okay. Let's look at the charging case. The charging case is a little bit trickier. I don't think I have that the circuit copied anymore. Switch over to the charging position. So I'm going to do a Kirchhoff loop again. And have positive E minus IR. And then I have minus Q over C. And the capacitor term is negative this time because I'm not going the other way through it. This time I'm going from the positive terminal to the negative terminal, so that's a decrease. I'm going to make a similar substitution as last time, but since Q is an increasing quantity this time, I don't need that explicit. I don't need the extra minus sign. So I just replace I with dq dt straight up. Isolate the dq dt. E minus Q over C. I need all of them over R. Like that. The solution to this differential equation is not as obvious as before because there's this other term in the way, but that's a constant term. E, the EMF of the battery, is constant, and R, the resistance, is also constant. Right? There's no Q. The only thing that's varying with time in this equation is Q. So the solution ends up being what I showed you before. Q of T going to be your maximum value of Q when you're approaching times 1 minus E to the negative T over RC. And if you don't believe me that that's the solution, go ahead and take the derivative of it, see what happens. You're going to get what I just told you about. So that's Q. If you're interested in delta V for the capacitor as a function of time, again, delta V is Q over C. So it's going to be that divided by C. But you still have the same 1 minus e to the stuff there. If you're interested in the current as a function of time, that would be from taking the derivative. I already know that the derivative is supposed to look like this, but I can substitute in the Q of t for the Q now that I know what Q of t is. And if you gather things up, you'll find that this one actually looks a little bit different, because instead of 1 minus e to the negative stuff, it is just e to the negative stuff again. I don't want to go through, this is already really long, so I don't want to go through the details of that, but it works out to be the same if you try it. Conceptually speaking, the reason that I has the same form here is that the current is produced by the fact that that you're closing the switch to allow the capacitor to begin charging. And as I said earlier, when the capacitor is empty, it's very easy to pour current into it. So the current is going to be strong in the beginning. And as the capacitor fills up, it gets harder and harder. And so the current needs to die out over time. And that means that it's asymptoting towards zero. So the functional form for the current specifically is always this decay form. Whereas the other quantities can increase. The charge on the capacitor can increase. The potential difference for the capacitor can increase. But the current always will decay. That is an important idea. I'll go ahead and write that. Current always shows the decay pattern. Even when charging the system. That's something that you can get to mathematically by going through all the process, but that's slow. You're better off remembering it. So again, the current has to stop. If the current flowed forever, if it reached a maximum value and settled there, then that would mean that the capacitor was getting more and more charge all the time, but it stops. Capacitor has to be able to fill up and stop. And that means that the current has to stop also. Okay, let me talk in a little more detail about the time constant. Suppose I am graphing, let's make this be Q. Suppose I'm graphing Q as a function of time. And I'm going to say that I am going up towards some maximum value of 100. So this is for the growth pattern. The graph that I just drew is the growth pattern. So the equation for this would be 100 times 1 minus e to the negative t over tau, where tau is equal to RC. So when t is equal to 0, the exponential term will be equal to 1, because e to the 0 is 1. So then I have 1 minus 1, which is 0, and so the function is 0. And indeed, the initial value of the function is 0. When t is equal to tau, then the exponent is going to be -1. And e to the -1 is roughly 0.3678, or like 37%-ish. I'm going to jot that down in the corner. E to the -1 equals 37%. So, when t is equal to tau, this becomes 100 times 1 minus 0.37, which is 100 times 0.63, which is 63. So one time constant, let's say it's here. One time constant gets me to about there. Which is around 63. Very roughly 2/3, but that's very rough. So if you wait for 1 tau, you'd go 63% of the way that you've got left to go. If I let t equal if I let t equal 2 tau, then I've got 1 minus e to the -2. I don't think I have that number handy. I don't have the calculator handy either. Let me stick that into Google. E caret -2. E to the -2 is 0.135. So 1 minus that is 0.864. I'm going to call that 86. So 2 tau, somewhere around here. Notice that that second time constant of mine, I didn't go nearly as far. I've now reached 86. So on the first time constant, I moved, my change was 63. And during the second time constant, my change was 17. To get from 63 to 86. And each successive time constant gives me less and less progress because I'm asymptoting toward 100. So during a single interval of length tau, during 1 tau, you go 63% of the remaining distance. So between tau and 2 tau, I only went 17, I said. But that 17 is 63% of what I had left. What I had left was 37. And I went 63% of that 37, which was 17. So you always need to think about how much further there is to go from the beginning of the time interval that you're looking at. And that is a little bit awkward. One of the reasons that HalfLife is simpler than these exponential time constants is that if you go half of the way, that means there's also half of the way left. So the amount that you went and the amount that remains, they're both half. But this one is asymmetric. So if you go 63% of the way, which means 37% is left, it makes it a lot harder to do a lot of the mental math, to do the simple mental calculations. But this rule of thumb that I've written here, that you go 63% of the way of the remaining distance. That's true whether you're doing a growth or a decay. It's also true even if there's not a zero involved. So like suppose I have a system where the initial value for Q is 10 and the final value is going to be 100. So the graph for that would look something like this. And the first time constant, tau, I have to go 63% of the distance that I'm going to eventually go. So I'm going to be going a total distance of 90 from the beginning of this interval until infinity. So I would find what's 63% of 90. That's the amount that I increase by, and that's how I figure out where I end up after the one time constant. That's if you want to do it like in this loosey-goosey kind of way. As an alternative, you could always just use the full function. Because of the fact that the time constant is asymmetric and not based on twos, personally, I find it easier to just plug things into the equation. That's rarely advice that I give, but I think it's probably safer. Like if you need to find the value at a particular time, use the function that tells you the value at any time that you plug in. I think that's probably the best way to handle it. The last thing that I want to do is show you one example of how they can make this kind of thing a little bit trickier. I'm not going to do a full analysis of this, but you're going to see some questions like this in the work. So I have two different resistors, RA and RB. This capacitor C. My battery E. So right now I have the switch open, which means nothing's happening. Capacitor's empty. If I close the switch, current is now going to start to flow. So current comes out of the battery. Some of that current is going to split and go down this path. Some of it is going to go this way instead. In the initial state, initial charging state, capacitor is empty. You can treat an empty capacitor like a wire. So that means in the initial state, the current through resistor A, which I will call IA, and the current through resistor B, which I'll call IB, are both easy to calculate. IA is going to be E over RA. IB is going to be E over RB. But that's only the values, the currents at time 0. IA is going to be constant, since if you did like a Kirchhoff loop for the battery and resistor A, those are the only things in the loop, so that current's going to be constant. But current B is going to decay over time as the capacitor fills up. Eventually, in the final state, while charging, IA is still going to be E over RA, but current B is going to go to 0 because the capacitor is going to fill up and you won't be able to send any more current into it. So the potential difference for the capacitor in that final state is going to be equal to the EMF of the battery, because the branch that has the capacitor, this branch that I'm highlighting here, that's in parallel with resistor A, and resistor A is connected directly to the battery. So both of those branches have a potential difference equal to the EMF. If I then open up the switch, that's going to isolate the battery. And then I've got this. So it's going to discharge by setting current around that way. And during this discharging state, realizing this isn't the problem that I thought it was, but whatever. In this discharging state, the time constant is based on both of those resistors, because both of those resistors are in the loop that I would have. So the initial current during the discharge is going to be E over RA plus RB, E being the initial potential difference for the capacitor, and RA plus RB being the resistance of the circuit. I didn't put an I anywhere, did I? So that's the initial current during the discharge process. The time constant during the charging process, you may have noticed I didn't mention. That's because that is actually really difficult to figure out. Because of the fact that there's more than one loop here, you can't write a simple differential equation the way I could in my example before. And so finding the time constant in a situation like this top circuit is actually extremely complicated. And the functions to describe like Q of t are similarly become more complicated. So if you get a circuit like this from the college board, they're only going to ask about the initial and final values. They're not going to ask about the behavior in between time 0 and time infinity. One last thing I want to do, which I thought was the one I was drawing, is similar to that other circuit. I'm not going to bother with the switch this time. Suppose we've got this battery, resistor A, resistor B, capacitor. In this case, the maximum voltage for the capacitor is not the EMF of the battery. So I have some current, I'll call current A, that goes that way. At the junction, it splits. Some current goes this way, some current goes this way. So the capacitor is going to charge up. Notice that in the initial state, when you think about this junction, in the initial state at time 0, the capacitor path has a resistance of 0, because we treat the capacitor as a wire. So in the initial state, current B is going to be 0. All of the current is going to go this way. And that would be the same as current A for time 0. But over time, current C is going to quickly decline. All of the current will get shunted over into resistor B instead. So at time 0, where did I write these things down? At t equals 0, current C is the same as current A, and current B is nothing. But at t equals infinity, current C is the one that's 0, and current B is equal to current A. Also, that initial value for current A, Z over RA, we don't need resistor B because nothing's going that way. But the final value for current A is E over RA plus RB. Because in the final state, both of the resistors are in the loop. And so now I want to go back to the maximum voltage for the capacitor. Capacitor is connected in parallel with resistor B. So the max delta V for the capacitor does equal delta VB. I'll put like a final. It's equal to that final value of delta VB. So that's going to be I final times RB, and I final I just figured out was E over RA plus RB. Or another way to think about that, we're just rearranging things slightly. But you can think of RB over total R. So that's sort of like what fraction of the total resistance RB makes up. So like suppose RB is a third of the total resistance. That means that the delta V here is 1/3 of E, for example. So anyway, you'll occasionally see situations like this where the final voltage for the capacitor is not the voltage of the battery. It depends on the layout. And even though when we introduce these ideas to students, we always use simple circuits where the capacitor just goes up to the EMF of the battery, it's important to realize that that will not always be the final voltage. And again, when you're doing your problems on this, you're going to see some circuits that are like that. But I wanted to put one in front of your eyes before you did any problems, just as a warning that the final voltage doesn't have to be the EMF. All right. So that's everything that I want to say. And good luck. We'll have time in class to straighten things out.